My name is Lingatharani and I'm excited to present this project along with my friend and teammate Vignesh. We both are graduate students in industrial engineering at Dalhousie University, and we are also share a strong professional background, having worked together over 5 years as a design engineer at Renault Nissan India. So our shared experience in automotive industry, especially working with plastic trims components, inspired us to take this project, a topic called scheduling optimization in injection molding plants for automotive trims. We took this opportunity in special topics in IE course under the professor Hamid Afsari to apply our real world knowledge in the simulation based academic setting. The core objective of the project is to optimize the production scheduling of an automotive trim spots by minimizing the make span while considering real manufacturing constraints like mold changeover and machine availability. Coming to the pictorial view, this pictorial view shows the complete bumper trims assembly, including both grained and painted parts. We have used the actual CAD model here to provide a realistic representation and better understanding for the various injection molded components involved in the assembly. So these are the key job types considered in our scheduling project. They include both grained and painted bumper types, like grained bumper and painted bumper, along with other injection molded trims components such as lower bumper, fog lamp bracket, radiator grille, rear bumper, side skirt, bumper carrier, fender flare and spoiler. Each of the parts has unique mold and processing time, which directly impacts the machine allocation and mold changeover direction in the scheduling model. So, in the introduction, the injection molding is a core process in automotive manufacturing, especially for producing trims components like bumpers, grills, and brackets. However, this process comes with operational challenges that impact scheduling efficiency. Some of the key challenges includes frequent mold changeover, shift-based release time of the job, and machines idle times. These constraints often lead to production delays and increased make span, making scheduling optimization crucial. In this slide, the main objective of the project is to optimize job scheduling by minimizing the make span, represented as Cmax. We modeled the problem as PM, precedence, setup time, and Cmax. Here, PM stands for three parallel machines, precedence is required, and SIJ it represents a setup time between jobs, and our goal is to schedule these jobs efficiently while reducing the total completion time. In our problem setting, we scheduled 40 jobs over a 5-day period divided into 3 shifts per day, covering 24 hours. So we used 3 identical parallel machines to stimulate the actual shop. So some key constraints we considered includes only one mold available per part type, setup delays due to mold changeover, and shift-bound release times, which restrict when certain jobs can begin. These constraints closely reflects real-world challenges in injection molding operations. This slide shows two important inputs to our scheduling model, the daily demand matrix and setup time matrix. For example, on day 1, we had 18 jobs for grain bumper alone, contributing a total daily volume of nearly 300 parts. To handle this highly output efficiently, proper scheduling and batching are essential. Setup time vary based on mold switch. For instance, switching from grain bumper to painted bumper takes 15 to 20 minutes, while switching from fog lamp bracket to radiator grill takes 15 minutes. So these values are stored in matrix and used dynamically to guide the machine assignments. In scheduling challenges, we encountered several challenges during this project. These includes sequence dependent setup time aligning job releases to shifts, maintaining an assembly-friendly job order, and handling high-mix spots with high-varying processing requirements. To address this, we tested three scheduling approaches: a greedy algorithm, a sorted processing time or SPT, and earliest due date or EDD. These are implemented using Python and Excel with Gantt chart visualization to track and compare the results. With that, I will now hand over this presentation to my teammate Vignesh Venkatapati, who will walk you through how each of these approaches was applied and conclude with the results.
Hello, in this slide, we go deeper into the working logic of the greedy algorithm and present the CMAC results from our scheduling experiments. The greedy algorithm works as follows. First, we sorted all jobs by their release times. Then, for each job, we looked for the earliest available mission. Before assigning it, we calculate the setup time required depending on the previously used mold on that mission. Only when both release times and setup constraints are satisfied, we assign the job and updated the machine state with the finish time and new mold time, so that this method is adaptive, efficient, and closely mimics how a real flow shop schedule might operate. Now, let's look at the result. Using the greedy approach, we achieved a Cmax of 105.85. In contrast, SPT resulted in 120.38 and EDD, which we have tried on our side, which matched with greedy at 105.85 but didn't offer any additional efficiency. These results reinforce the idea that greedy algorithm not only respects real release times and setup constraints, but also optimizes machine utilization effectively. It outperforms SPT because SPT doesn't factor in setup or release delays. It purely prioritizes short jobs. Greedy, on the other hand, balances all critical scheduling elements. Slides highlights the Gantt chart output and the key insights we gained from visualizing the job schedule. First, looking at the Gantt chart on the next slide, the jobs were effectively distributed across all the three machines, ensuring that no machine was left idle unnecessarily. We also notice clear mole changeover, which are handled efficiently by the greedy algorithm. Additionally, all job assignments are properly aligned with the three shift windows, confirming that our scheduling logic respects real-time operational constraints. Now, on to the insights. Setup time emerged as a critical factor here in determining the overall efficiency. If setup transitions are not considered carefully, even well sequenced jobs can result in large idle gaps. The greedy algorithm, by evaluating release times, mold setups, and machine availability, offered an optimal strategy which aligns closely with what would be needed in an actual factory. Then, EDD, which was helpful in prioritizing deadlines, it didn't reduce the make span more than the greedy approach. However, it would be useful in deadline sensitive environments. This chart shows the job allocation when we use the shortest processing time strategy. While SPT is useful in many classical scheduling problems, notice some inefficiencies here. Jobs are bunched based on processing time without considering mold changeovers or job release shifts. As a result, we can see idle times, long setup transitions, and sometimes jobs starting late even though machines were free earlier. This demonstrates that SPT fails to account for the real-world constraints of injection molding operations. This Gantt chart represents the outcome of the greedy algorithm. Each job is slotted into the earliest available mission, but only after evaluating release time and setup time from the previous mold. As we can see, this approach results in minimal machine idle times and efficient use of molds. It aligns with shift-based release, making it a more practical solution for industries with such constraints. The smoother mold changeovers here contributed to the lower Cmax value. Here, we present the max span value for the SPT approach, which came out to be 120.38. This value is considerably higher than what we achieved with the greedy approach. This confirms our earlier Gantt chart analysis that SPT doesn't effectively reduce mold changeovers or accommodate with real-world timing constraints. Using the greedy strategy, we successfully brought the Cmax down to 105.85 weekly hours, which was the best among the three techniques. This value confirms that greedy approach strength in handling both release time logic and setup time minimization, making it well suited for high mix, high volume scheduling problems. This output shows the actual machine assignments, start and finish times from the Python simulation of the greedy algorithm. The job allocations are efficient and the transitions were based on the setup time matrix. This not only helped to minimize the Cmax but also ensured shift constraints and mole changeover efficiency were preserved. Here is the Python output for the SPT strategy. While the jobs appear to be shorter in duration, we can notice that many start times are delayed unnecessarily due to ignored release constraints and higher setup transitions. This again confirms that processing time alone is not sufficient in environments where mode changes and shift constraints are dominant factors. Based on our experiments and analysis, we have gathered several key learnings. Greedy scheduling performs best under complex and real-world constraints. Shortest processing time algorithm might be theoretically optimal for simpler cases, but not when more setup and release times are critical. Third, the importance of visualization tools like Gantt charts become evident that they help to validate schedule feasibility and identify bottlenecks. Overall, we observed that practical scheduling must be tailored to account for flow-sharp realities such as part transitions and operator shifts. To conclude, this project offered a practical perspective on scheduling challenges in an injection molding facility. We modeled a real-world system with precedence constraint, shift-based releases, and setup times. The greedy heuristics, although simple, turned out to be highly effective and outperformed classic techniques like SPT and EDT. This model can now be extended to support even more advanced features like dynamic batch scheduling or machine maintenance windows, but it already provides a strong baseline for operational planning and in then automotive manufacturing. These are the references which we have used. Thank you for giving us the opportunity to work on this project. Have a nice day.